Hello, everybody, and welcome. This is Friday. Beautiful day outside in Toronto. It's 11:10, so why don't we just get going? So the plan for today is we're going to start in on Chapter 5 on circular motion, even though Chapter 5 material will not be covered on the October 13th midterm, but it will be on the October 27th midterm, which is a multiple choice one 2 weeks later. So it is good to learn. Just bringing up my participant window so I can see you and so I can see the chat. Okay. And today, a part of the plan is we're going to be taking a 10-minute break at sometime in the middle of the class to do a group discussion quiz on Microsoft Teams. So hopefully that goes well. Yes, I wanted to launch a poll. So I have these, this way of making a filter on my face. So you can choose which one you want. I will go with whatever gets the most votes. A is pig snout and ears. B is chevron mustache. C is goatee. Blaze royale. D is goatee circle. And E is red lipstick. So think carefully about this because I'm going to leave this filter on for the rest of today's class. And then when we come back on Wednesday, I'll take it off again. Yeah, I kind of saw where this was going. Come on. Yeah, it's okay. This is a democracy, so I think you guys should be able to choose. Sorry, it's a bit of a landslide I'm looking at here, and I think you might be able to guess. I'll wait till 90% of you vote, just in case there's any last minute changes. There's also people coming in, so welcome. We're voting on whether or not Harlow gets a pig snout today. Okay. So I'm going to end the polling. And so 55% of you definitely voted for pig snout. So let's look for that. More. What's on video? Video filter. Okay. So hopefully that is working. Okay. Okay. So next thing is, I wanted to discuss the practicals schedule. It's just a little bit confusing. So everyone has finished the first 3 weeks of practicals. And you may notice, and you probably hopefully know that if you're in a Friday practical, you actually did week 3 last week, and there's nothing going on today. So it is a bit tricky. It was for the first 3 weeks, Friday came first and Thursday was last. But starting next week, the Wednesday practical students will be the first and the Tuesdays will be the last. Anyway, bottom line is that there's no practicals today. Hopefully you noticed that. And also next week, there's no practicals on Monday because it's Thanksgiving, and there's no practicals on Tuesday of next week. That's when you're going to be having that test. So we're going to start up this whole thing as per regular it will be Wednesday, October the 14th will be the start of this next practical schedule, the week 4. Hopefully that's clear. Some of the people in the chat are liking the pig ears, so that's good. Yeah, if you do the team up quiz later, that's okay, but I would like to do it today. But it's going to be open all weekend, and it is possible to do it on your own if you want. It's just not as fun. And Marcia, would you like to unmute? Question?
My bad. I didn't realize I raised my hand.
That's okay. No problem. Okay. Good. You're good. It was good to hear someone's voice to know I'm not totally alone. Okay. So I want to watch a quick video from the book. See if this works on the power on the Zoom to display a video. But there are 2 experiments in this video. One is that there's a bowling ball rolling on a floor as observed from above. And you are asked to tap it with a mallet and make the ball roll in a circle around a central spot. I think it's the drain in the floor. What the person finds really quickly is that you have to tap it towards the center of the circle, or else it always kind of goes, goes on tries to go on a straight path. The second experiment is you hold a bag by the handle and you swing it in a horizontal circle at a constant speed. You observe that your arms pulling the bag are angled down with respect to the horizontal. So let's try to look at that video. Hopefully you'll be able to see it. Maybe I have to tap it. Oh, here we go. Okay, so that was him hitting the bowling ball. And there's a side view. Okay, so those are the videos. The free body diagrams for the bowling ball, you've got, if you look at it from the side, then there is a vertical normal force and a vertical downward force of gravity. But since you're just hitting it sideways with the mallet is hitting it in this direction, which is toward the center of the circular path. So there's three objects that are interacting with the bowling ball and putting forces on the bowling ball. There's the floor, which is puts a force upwards on the ball. There's the earth, which pulls downwards on the ball, and there's the mallet, which hits towards the center of the circle on the ball. And if it goes over to the other side, where it is over here, then the force is still towards the center. It's always kind of directed inwards. And so there's kind of, in these, when you get into this chapter 5, there's sort of usually two perspectives that happen. There's kind of a downward view, and then there's a side view. So things are getting into 3 dimensions here. Here's that backpack one. 2 forces are exerted on the bag as it moves in a circle. It's just the earth pulling down, that's the gravity force, and the tension from the person, which is pulling at an angle with the vertical. So if you think about it, it's not actually dropping down or up. It's not accelerating down and it's not accelerating up. So the vertical component of the force you exert on the bag must balance the downward force that the earth exerts on it. Okay, so consequently, the sum of these 2 forces actually points towards the radial center of the circle, which is actually the same as what happened with these, is that in this case, the 2 vertical forces canceled and all the force was towards the center of the circle. And in this case, the y component of this force of u on the bag cancels out this Fy on bag in the y direction is equal in magnitude to the Fe on the bag. Okay, they cancel out. And the only thing that's left, the net force, is going to be towards the center. So I'll draw that sort of, we don't usually draw the net force right on the force diagram though. We can draw it over here. Net force is towards the center. Okay. So our hypothesis is that when an object is moving in a circle, the sum of all the forces exerted on it by other objects is directed towards the center of the circle. And we can test it. If you remove the inward forces, does the object cease to go on a circular path? So I'm going to do a little demonstration. So we can do a little vote on it here. You have this one. Find my notes here. Here it is. A ball which rolls along a frictionless track on a horizontal table as seen from above. So you're looking down from above on this table. The track is curved in 3/4 of a circle, and the ball rolls clockwise around this track and then emerges onto the flat frictionless table. And again, gravity is kind of into the page here, so there is no gravity really. Which dashed line most closely represents the path of the ball as soon as it emerges from the track? So I'll let you make a prediction and then we'll try to do an actual demonstration of this. Okay. All right, I'm going to end this polling. We'll look at the chats in a second here. So most people are saying C. Let's actually see what we can actually see if we stop this share. So there's me, I'm hoping. And what I want to do is point the camera around, swing it around, and point it down at the table here. So I've set this actually up for you guys. Hopefully you'll be able to hear me when I go over here. I'm going to try to speak a little more loudly, but this is a flat track. If I put a ball on there, Pius has set it up so it doesn't roll. It just rolls in a straight line, no matter where you go. So if I put it in the track, did you see that? You want to do it again? As soon as it emerges from here and the inward force from this wall stops putting inwards on the ball, it tends to grip the edge, so if there's a normal force pointing perpendicular to the wall as it's here, as soon as that normal force goes away, it just goes in a straight line. If you don't believe me, whoop, you can see it goes exactly on a line, which, oh, just drop it. It's okay. All right, so there you go. So good. And I wanted to also deal with some of these questions coming in on the chat. It says, so actually someone asked about the bag. Is the normal force on the bag just combined with the tension? So in the case of the bag, I just think of it as tension, since you're holding on to, I guess, the string that's holding the bag, and you're pulling on that string. It's not really a normal force, because normal force is always kind of pushing. And in fact, there's nobody pushing on that bag when it's going around in a circle, right? It's not in contact with anything. There's just a pulling force. So it's just two forces, just gravity and tension. And then as far as this track, the track is a wall. And if it wasn't for the wall, the ball would just go in a straight line. But the wall is there pushing on the ball, and that's a normal force. Okay, every time you have a pushing force from a surface that's perpendicular to the surface, so in this case, it's towards the center of the circle, that's called the normal force. Okay. Some people are getting a little disturbed by this pig thing, but that's okay. You guys can handle it. So let's go back to my share screen. Okay. All right. So yeah, C is the tangential velocity at the moment that it is no longer accelerating. So the inward force suddenly goes away. And then you just go on in a constant velocity in a straight line at whatever your instantaneous velocity at that moment is. Once again, I need to be able to see the chat. I need to be able to see participants. Okay. I do see a couple of raised hands. I've got Josephine. Do you have a question?
Hi.
Hi.
Can you quickly re-explain why it's C? Because I'm looking at it from like where it comes out the other end, and I can't figure out why it would go to the right.
So the idea is just that, so you're looking down on it from above. So at any point, its velocity, so it's going in a circular path. At any point, its velocity is tangent to that circle. This is V, right? And so when it's right up here, the velocity is tangent, okay? But the thing about as soon as it emerges from the track is at that point, there is no inward force. So here there's an inward force all the time, which is causing it to accelerate. This is F, F, F. But as soon as you get to this region, F, equals 0. And so velocity becomes constant. It doesn't want to continue going in its circular path because you've suddenly removed that inward force. That's sort of the idea. It's a good question. Okay, so now is the time. It's 11:25. We're going to take around 10 minutes here. I want to get into team up. So it's 3 multiple choice questions. They're all from chapter 4. We can look over them right now, actually. Each question is worth a maximum of 5 points. You can guess more than once. If you get it wrong, you lose some diamonds each time you submit a wrong answer. So and they're just homework points, so it's just supposed to be for fun here. The first question is about an ice cube which slides down a frictionless ramp. The question is going to be, how does N, the magnitude of the normal force, compare to the force of gravity? The second question is about projectile motion. It's asking for projectile motion with no air resistance. How does the horizontal component of the projectile's velocity change with time, or does it? And then question 3 is about these 3 blocks. And what's listed here is the weight of each block, or the force of gravity from the Earth on each block: 10 newtons, 20 newtons, 100 newtons. So you can see they're different masses. And you're asked to compare the pulling force here, which is accelerating the whole system, to the tension in this rope connecting these 2 blocks, to the tension in this rope connecting these 2 blocks. So that was your preview. You now have 10 minutes. So I'm going to put myself on mute for 10 minutes. So right now what you should do is open up Microsoft Teams, and someone, the most recent facilitator, should place a video call to all 3 or 4 members of your pod chat. Hopefully you know how to do that. The first step is to decide who will be the team up driver. And then all of you must also log into Quarkus at the same time. If you're not the driver, then just wait for a minute. The driver, click on the team up quiz in module 2. Click go to tool and click create a group. That'll give you a little session ID. So go back into Microsoft Teams and type that into the chat of the Teams, or say it. And then wait, don't drive off alone. You're going to see the first question, but wait for everyone else to join in, and you'll see them come into your team up. So non-drivers, you have to wait for a minute till your driver tells you the session ID, and then you go to the team up quiz, click go to tool, and click join session. Don't create a new session, just join it and type in the ID your driver gave you. And then once everyone arrives from your room arrives in the team up, then you can start doing the questions one by one. And please achieve consensus before the driver submits. So I'm going to leave on the chat, and I'm going to put myself on mute for a little bit. Where am I? So go, have fun. Okay. My timer just went off. I don't know what to beginning at the very end means. Again, when I go on to team up, I see a different thing than what you guys see. But hopefully it went okay. It was a bit crazy because when you're in the chat window, you have to type to all panelists and attendees if you want anyone to know what you're typing. So I was typing like crazy for about 5 minutes trying to answer everyone's questions, but no one was seeing my answers, so that was ridiculous. Okay, so if you did not finish, or if you are watching this on YouTube later, you have the rest of this weekend to complete the team up. And I would encourage you to go on Microsoft Teams, message your pod mates, and set up a time when you can get together and do this together. Or you can just drive off on your own and submit it as a single person, and that's fine as well. You get the full points either way. If you feel like leaving your Microsoft Teams open for the rest of today's class, that's fine. I actually have 2 more poll questions to do in this Zoom call today, so you might want to discuss them. That's fine with me. I remember that when I was a student, I used to find friends in my classes and sit beside them, and kind of we would whisper to each other. And I don't know if that's rude or not, but it was a lot of fun, and I had a lot of great conversations that way, and I think it really got me motivated to get up and go to class. And so in COVID, you can't really whisper in someone's ear, but you can have a Zoom call open, I guess, on the side, but not if it's too distracting. The idea with the ice cube, basically what I'm seeing is that if this is that normal force, and then you could do, I guess, a surface on the cube. And if this is the downward force of the Earth on the cube, then the acceleration is only in this direction. So if you do what I like to do and define y to be perpendicular to the surface and x to be in the direction of the acceleration, then what this means is that the acceleration in the x direction equals 0. Switch to blue here. So that means that the sum of all the forces in the, oops, wrong, that's not correct. A sub y equals 0, so the sum of the forces in the y direction equals 0. And so that means that you have to do this whole thing where you've got a right angle there, and this is, here's your theta, here's your theta. You end up with, this is normal force up minus Fg times cosine of theta, I think. Anyway, the normal force equals Fg cosine theta. Cosine theta is less than 1 but greater than 0, so this is less than Fg. So I like B. That makes sense? And then this projectile motion one, the whole idea with this one was going to be that the acceleration in the y direction is the negative 9.8 meters per second squared. It's a projectile. The acceleration in the x direction equals 0. That means that Vx is Vx0 is a constant. But it's not 0 unless the thing's going straight up and straight down. Okay. So it can be. And this last one, so I would, if I call this M1 and this M2 and this M3, for example, the way I would compare the tensions T1 and T2 is I would define the system, the whole thing is accelerating towards the right with some acceleration, right? Define system is M1. So then what you've got is you've got normal and you've got gravity, but your only horizontal force is T2. So only horizontal force is T2. So T2 is the whole sum of the forces, and that's equal to M1 times A. And then the other thing you can do is you can define the system to be M1 plus M2. Oops. To figure out what you're going to do about T1. So if you draw a little dashed line around the whole thing there, then Your force diagram has got normal and FG, but the only external force is T1. The only horizontal external force is T1. So T1 is equal to the sum of the forces is equal to, and I'll put that in the X direction or something, M1 plus M2 times that same acceleration A. So that's why T1 is greater than T2, because T1 is accelerating both blocks, M1 and M2, if you consider them to be the system. There's only one external horizontal force on that system. If you just consider the system to be M1, then the only external force is just from T2. So I like D for that one. A bit tricky. Good. I hope that went all right. Let me take a look at these here. Okay. I've got Fang King, you have your hand up. Did you want to ask a question?
Sir, I have a question for previous slide.
Yeah.
But can we go back to the ball rolling in a circle?
Yeah,
This one.
from the demonstration?
Yes.
This one?
Yes, this one. Like my question is, why is not A? Because like this is also straight, right? And
Yeah.
for I saw you make a little experiment, and the ball it's not like going exactly to the right. It's like there's a angle, like I remember.
Well, I think the idea is that when you are on a circular path, the instantaneous velocity is tangent to the circle.
Okay.
It is a bit tricky. I see what you mean. A and E both have, so A, C, and E are all three of them are straight lines. So
yes.
all of those are allowed, but which one of those is tangent to the circular path just as it emerges from the track, I guess is the question there.
Okay, yeah, thank you.
Does that help? Sure.
Yeah, that helps. Thank you very much.
You're welcome. And Emanuela, you had your hand up?
It was literally the exact same question as her.
Okay.
Thank you, though.
You're welcome. And Ivy Park, did you have a question?
Ivy, go.
Oh, sorry. Yeah, I forgot to lower my hand. Sorry.
That's okay. I remember you had it. Hopefully, it worked out with the team up from before. And Thea, did you have a question?
Yes. I have a question about the midterm assessment. Like, can we like leave out all units during the equation and then only write the units for the final answer?
Can you speak just a little louder? You're asking about the midterm?
Yeah. I said, can we like leave out all the units during the equation and then just write the units for the final answer?
Yes, absolutely. Yeah, that's right. That's a good point. Is keeping all the units in every single step of the equation is not required for the midterm. That's a good question.
Thank you.
To help, sure. It's hard to get through everybody here. Let me do one more from Naomi and then I'm going to continue. Naomi, did you have a question?
Hi, I have a question about the ball experiment also. What would happen if there was like no exit and the ball just kept rolling in a circle? Like what would happen to the velocity of the ball?
Well, if it's frictionless and if it's a horizontal plane that you're looking from above, it would just keep going around in a circle. In real life, there's friction, so it'll slow down. So there's sort of two forces on it. There's the normal force from the wall, and there'll be a kinetic friction force or some sort of rolling friction that's going opposite to the instantaneous velocity, which will eventually slow it down.
I see. Thank you.
Yeah, sure. Okay. So I do want to continue and do a couple more things because I had a couple ideas for some forward here, some polls. Yes, this is my idea that it's a bit weird and you're gonna have to deal with this at some point. So every curve has a radius. So here is a bird's eye view. Let me just get the lights back on. Of the intersection of Highway 427 and Highway 401. So the little off-ramp here is like a circle, and it has a radius of 75 meters. But any portion of the highway that is curved, you can look at this tiny little portion and fit that bit of the path to a circular path, and that will have some radius. And if it's less curvy, then the radius is increased. So this part of this path here, you're not turning as much. So the R value for that, which is from here to here, is 410 meters. And if it's even less curvy, like almost a straight line, when you fit it, you get 730 meters as being the radius of that part of a circular path. Now you don't actually stay on the path, you're only on that portion right here, okay? And you're only on that portion kind of right here. So often, and when this will come up a lot actually on Wednesday when we come back, is you'll get V squared over R. Anytime you're turning, you're gonna have V squared over R as your acceleration, and this is what the R means there. So here's a poll. What horizontal force acts on the car to keep it on a curved path? So you're on the highway, you're turning left here, you're going, I guess, up and this is your back view. Let's do a poll. Is it A, gravity, B, normal force, C, kinetic friction, D, static friction, or E, rolling friction? And Siet asked a question, how does Quarkus know who to give the credits to? So Team Up is designed so that everyone in the team that joined that group gets the same mark, whatever the driver submitted. Let's look at this one. So 43% of you voted for static friction, and that is exactly correct. That's what I was looking for there. If you look at the back view, static friction is actually pushing the car to the left if you're turning it, and if your velocity is sort of into the page. It's a bit difficult to view, but that's kind of like, it's the same, you always need an inward force to keep anything on a circular path. Could be a string, could be that mallet, someone hitting you from the side or something, could be static friction. But my point is, if it wasn't for static friction, if you had a perfectly icy road, then you would just go on a straight line and you would end up in the ditch. So you need static friction between the tires and the between the road and the tires in order to keep yourself on that path. So if you're on a, let's draw a path here. Let's draw it in blue. This is a path. And you have some particle, and let's put the particle right here, for example. And I can draw, sometimes they draw in green, the velocity vector. So the velocity vector is tangent to a curved path. This is instantaneous velocity, otherwise known as velocity. Okay. If you define, I'll maybe do this in blue or black, I guess, define X and Y, so that X is parallel to the V direction, the velocity direction. Then what you have, I think they like to use orange for the acceleration. If this is the acceleration, then what you can do is you can sort of split acceleration into its Y component and its X component. Okay, so the A sub X is the component of the acceleration that causes the object to speed up, or like in this case, speeding up, or if it was angled backwards, with a component that's negative to the velocity, it would be causing it to slow down. A sub y is the component of the acceleration that causes the object to change direction. So in this case, it's sort of positive. That means the whole thing is turning to the left. And a little instant later, the velocity will curve a little bit. So an object changing direction always has a component of acceleration perpendicular to the direction of motion. So here is a situation where speed is constant. So the acceleration, A, has a 0 component in the direction of V. Okay. So, and what this means, let me switch to black, I guess. So it's not speeding up or slowing down. Time's okay. Yeah. It's always just pointing inward towards the circle. And so let's do another quick poll here. Polls. So a car is traveling east at a constant speed of 100 kilometers per hour, but the driver has turned the steering wheel so that it is turning left. It's following this curve in the highway, and you're seeing it at the instant that it's sort of at this point in the curve. But at this instant, the velocity is exactly east. What is the direction of the acceleration of the car at this instant? Is it A, exactly north, B, exactly east, C, somewhere between north and east, and D, somewhere between north and west? So it shouldn't really say northeast. C could be anywhere between north and east, and D could be anywhere between north and west. E is none, the acceleration is 0. We'll discuss this one a little bit more when we come back on Wednesday. Okay, give you 10 seconds. Click in. That's correct. This is not going to be on Tuesday's midterm. It will be on the October 27th midterm. But yeah, not this one coming up. So let's do end polling. Share results. So 51% of you voted for the exact same thing I would vote for, which I think it's going exactly straight north. Idea being is that if there was any component to the acceleration in the east direction or in the west direction, then it would be speeding up or slowing down. So it has to have a 0 component in the direction of the instantaneous velocity, and that's what causes it to turn, but at a constant speed. So people are asking on this thing about on the chat about the midterm assessment. There will be 2 problems that you must solve on Tuesday. The solutions must be in your handwriting and written upon the answer template sheet for something very similar. You'll see both problems at once, starting Tuesday, October the 13th at 8:10 p.m. Toronto time. Both problems are from chapter 4. You have 30 minutes to write out your solutions to both, and then there's an additional 5 minutes which you should allow for uploading the file. And you can practice with this if you want with the format using the chapter 4 pre-quiz new format. No one's going to mark that, I think, because my markers are focused on the real chapter pre-quiz, chapter 4 pre-quiz. But that's just there for you to try to practice at it, at uploading. All uploads must be complete by 8:45 p.m., 30 minutes after the start time. You may upload both solutions as a single PDF if you wish, or 2 PDFs, one of each, or 2 JPEG images. Please be aware of your file sizes. Hopefully, if you can see them, they're measured in kilobytes, not megabytes. You know, just taking a picture of a single page should never be in more than a megabyte or 2. It should be a lot less. Oh, I've provided free answer template sheets. They're just outside here. If you happen to be near 255 Huron Street today, on Friday, October 9th, between now and about 4:30, when I'm going to go home, I printed out 50 blank copies of the answer template sheet. So you can feel free to take as many as you'd like. I'll look out my window. If it gets empty, I'll refill it. So you go to 255 Huron, go up the stairs. You'll see a box over here. That's my window to my office. There it is. It says Physics 131 Harlow on it. And if you look inside it, you'll see a bunch of just blank answer sheets. So you can grab those if you don't have a printer. And I have a good printer, so I can print out more. April wanted me to tell you that every student has a 52 megabyte file capacity on Quarkus. So if you're running out of space, you have to either delete unnecessary files, or you can move these files to OneDrive and then submitting choose OneDrive and selecting a file from there. So I can look at questions, but don't forget to do this quiz on Tuesday evening. We are not meeting on Monday. There are no practicals on Tuesday either, actually. The whole class resumes its normal schedule starting on Wednesday, October the 14th. So before then, please read about this radial acceleration. This is that R in that the curved path. V squared over R is the radial acceleration towards the center of the circle. And we're going to work on how we solve these circular motion problems. So I'm wishing everybody a happy Thanksgiving. I'm going to turn off the recording, and then I'm going to look at hands. Here's my recorder.